Hello. I'm going to continue on with maximum power transfer using Thevenin's theorem and create this video called 8GG. I'd like you to get your lecture notes out, pages 171 through 173, and I want to take a look here at expanding on this Thevenin's theorem with maximum power transfer. If you remember, we had this circuit here and we used Thevenin's theorem to find this output voltage. And we went through page 171 and 172 in the previous lecture, and we come up with the Thevenin equivalent circuit looking like this. And we pointed out that if we want to get maximum power from this Thevenin equivalent circuit to the Thevenin load out here, what we would need to do is come up with a load impedance that was the complex conjugate of the Thevenin impedance. So the Thevenin impedance here was 0.8 plus j 1.6, and the complex conjugate of that was 0.8 minus j 1.6. So if we ended up putting that on the output, you would see that the reactive terms would cancel and we'd end up with a match on the resistance, 0.8 equal 0.8. What I want to show you now is how to calculate that maximum power. There's an equation that we used, and it was this equation right here. We used back, I think it was in chapter 5, and we said the maximum power, or true power, in the load was equal to E Thevenin squared over 4R Thevenin. That was in watts. We just took the Thevenin voltage, we squared it, and divided it by 4 times R Thevenin. Very easy to prove if you look back in your lecture notes. Well, there's another equation we can use, and that equation is the average power max that can be delivered to the load is E Thevenin squared over 8 times R Thevenin, and that's in watts. And you might say, well, which one of these equations do you use? But remember, this was the DC equation. That E Thevenin up here had to be DC, or it had to be the RMS or effective value. So if you're going to use this equation in the numerator, in the denominator, and have a 4 times R Thevenin, you needed to make sure that that E Thevenin voltage was RMS or effective. In essence, it was the DC equivalent value, and then that would work. If you're going to use peak values, if E Thevenin is in peak, and as we work through these problems, I think you can see here when we work through all these problems, we're working with phasors, and the Thevenin voltage is 11.96 at an angle of 126.8 here on page 173. You know that in phasor notation, that's the maximum or peak value of voltage of the sine wave. So if you're going to use this equation right down here, you have to make sure E Thevenin is a peak value or a maximum value. I don't want to write the word maximum here. I don't want you to get it mixed up with maximum power. I think it's pretty easy to see this. If you remember, the RMS value of voltage is equal to Emax divided by the square root of 2. Or it can be written as Emax times 0.707, but I'm not concerned about that. I'm going to keep it in this form here. So if I can go up here and I can replace this E Thevenin RMS with Emax divided by the square root of 2 right up here, you can see both of these get squared, and it puts a 2 in the denominator times the 4, and that's how you get the 8. These are identical equations. They give you the same value, but the value for this formula has to be RMS, and the value for this formula here has to be the peak value. We're going to use this one with sinusoids because we end up with a peak value for the Thevenin voltage. So if we go back to that original problem on page 173, I want you to go ahead and calculate what the maximum average power is that we can deliver from this Thevenin circuit to this load impedance out here using the equation that I gave you. And if you do that, you should come up with that for a solution, 22.35 watts. So now you know how to calculate the average maximum power that can be delivered to the load impedance in sinusoidal circuits. There's some examples here that I wanted to point out. This is in the next chapter, but I'm going to introduce it here. It's pretty straightforward, and we're talking about Thevenin's theorem at this point. Here we have a circuit, and I want to find a value of ZL here for maximum power transfer from this circuit to ZL, and I want to find that value of power. Well, you have all the tools to do this. You remove the load resistance, and since both of these sources are independent sources, you can reduce them to zero looking in here from the right-hand side. I think you can see that the Thevenin impedance is 2 in parallel with J2. It's just 2 in parallel with this J2, product over the sum of this, and it's a minus J2 because of this capacitive reactance up here. So you should be able to figure that out. You should calculate almost by, well, not by inspection, because this is product over the sum. You have to do a little phasor algebra here. But you should get the Thevenin impedance is 1 minus J1 ohms. So the value for the load impedance for maximum power transfer is the complex conjugate of that Thevenin impedance, which is going to be 1 plus J1 ohms. There's the answer. And what's the value of power? Well, what you need to do is find this open circuit voltage out here. I'm going to find this open circuit voltage now. And I'm going to find it using superposition. I'm going to reduce this source to zero and find out what that voltage is right here, because there's no current flow. This is an open circuit. So whatever the voltage is at this point, that's the voltage out here. So I'm going to find this open circuit voltage, or this node voltage, due to this source with this reduced to zero. And then I'm going to find what that open circuit voltage is at that node with this source with this reduced to zero. And this is where I do it right here. The open circuit prime due to the 24 volt source it's just the voltage divider rule. 24 at an angle 0 times 2 at an angle of 90 divided by 2 plus J2. I get this value. The open circuit double prime, that's going to be due to this source up here. Again, this is shorted, so it's just the voltage divider rule of this. It's a negative value times this divided by the sum of the two. That's the voltage from this point to this point. It's the voltage across that resistor. Anyhow, that's it. You should see that. And I end up with this value. Now I just have to add those up. So I convert both of these to rectangular form. I just add these up. And when I do, that's my Thevenin. That's my Thevenin phasor voltage. It's 18.98 at an angle of 71.57 degrees. Well, we don't need to worry about the angle because that average power delivered to the load is simply that Thevenin magnitude squared divided by 8 times R Thevenin. It's 45 watts. You should understand that. That was problem E97 in my textbook. Let's look at E98. Same thing here. Here we have a circuit. I want to find the value of ZL for maximum power delivered to ZL from this circuit. I want to find that value of power. I work through the problem. I get my Z Thevenin. That's my value of Z Thevenin. Complex conjugate of that, that's what the impedance of the load has to be for maximum power transfer. I find my open circuit voltage out here of this circuit up here. I just find the open circuit voltage. This is going to provide nothing more than a voltage. That's the only thing this is going to provide is a voltage. So all you have to do, it puts no current into this circuit. This puts no current into the circuit. That's an open circuit there. These Thevenin circuits are not that difficult to work with. So my only current through this element here is going to be because of that source. So I used a voltage divider rule to get a voltage at this point due to that source, and I just added this on. That's all I did down here. I end up with my Thevenin voltage. I take that magnitude, I square it, divided by 8 times R Thevenin. R Thevenin was 2 ohms up here. And I get 45 watts. You should understand problem 9.8. Then finally, there's an exercise in the book. If you understand this problem, if you can work this problem out, it's about as difficult as I would give you on an exam. And you should work this out. Everybody should know how to work that problem. Let's take a look at it. Here's the circuit. That's what the circuit looks like. And I want you to find the value here of Z sub L, the load impedance, for maximum power transfer from that circuit to this load impedance, and then find the value of power. Well, you remove the load, you remove Z sub L here, and you look in, but you cannot reduce these sources to zero by shorting them, because that is a dependent source. Anytime you see dependent sources, you cannot find Z Thevenin the way we found Z Thevenin in the past two problems. You have to find it through this ratio. Z Thevenin is equal to the open circuit voltage divided by the short circuit current, which is nothing more than the Thevenin voltage divided by the Norton current. You're going to have to find Thevenin anyhow, the Thevenin voltage, so you're almost there when you get through this problem. So here's my solution, and I'll just post it. I'm gonna first find E Thevenin, the open circuit voltage out here, by nodal analysis. So I assigned my currents right there. You can take a look at that. I assigned this current. The thing you have to be careful with on this problem, and this problem has a little bit of everything. The author gave you this polarity, plus to minus. The author has given you this polarity for V sub X. So you have to define your current with that passive convention from plus to minus. This current I called IX has to flow up because the author gives you that polarity. That's what's going to catch you in this problem if you're not careful. Otherwise, I'll write my first level equation right here. This is an open circuit, so I choose 0. I take my time. I use nodal analysis. I find the least common denominator. I multiply through, and I get this equation here. You should be able to get down to that point. By inspection, V sub X is equal to a -4 minus V open circuit prime. I called this V open circuit prime up here, but you know the V open circuit prime is going to be equal to V open circuit because this is an open circuit, no current can flow, so the voltage here is going to equal the voltage there. I just didn't want to confuse you by writing this as V open circuit here. So that's why I called it prime. So you can take a look what Vx is equal to here. Just look up here. What's Vx equal to? You have to start on this side. On this side, it's you're down 4 at an angle 0. That's -4 at an angle 0 minus V open circuit divided by 2. Well, that was the current. All I'm looking for is the voltage there. I'm just taking the voltage here minus the voltage there, and that's what I get. I substitute this into the equation up here. I've simplified. I get my open circuit voltage being equal to this -3.16 at this angle. I get rid of those negative signs. I added 180 degrees or subtracted 180 degrees. So my E Thevenin is equal to my V open circuit, which is the V open circuit prime. Turns out to be equal to 3.16 at an angle 198.43 volts. Almost done with the problem now. But just for fun, I'm going to find the open circuit using loop analysis in case somebody would have wanted to do this. Some students has asked me in the past, well, I use loop analysis here. I made a loop here, I1. I called this I1 going around here, and I did loop analysis, and I can't get that same answer. Well, let's see. Now, keep in mind, you don't have to do this if you already did through nodal analysis. But in this case right here, by Kirchhoff's voltage law, around loop I1. Well, here's loop I1. I'm going to call this current from this point clockwise I1. I'm going to call, that's the only current I'm going to have, is that current called I1 going around here. Remember how I told you to do this. You do a plus Vx minus J4. Then you stop and think. It's times I1. That's the voltage there. Now, if that was a capacitor of minus J4, you would write this as a plus Vx minus a minus J4. Then stop and think, times I1. You have to be careful with that. The initial minus comes from it's a passive element. But anyhow, if you go ahead and you write the equation, that's what the equation looks like. And since V sub x is equal to a minus 2 I1, That's another place students make their mistake. Take a look at that circuit, that original circuit, and make sure you can see that V sub x is a minus 2 I1, the way we defined I1 in the polarity that the author had. I make the substitution and I come down here and I find I1. I have one equation with one unknown. I can find what I1 is, and I can go up here and make the final substitution for I1 to find Vx, and that's all I did here. And I come down and I get the exact same answer. There's my solution. Right there. Yeah, let's see if I can't get all that on there, but you can pause the video and look at that and make sure you can get it. And there's my final solution right there. I get the exact same value that I got before. That open circuit voltage I got using loop analysis. And if you take a look, it's the exact same open circuit voltage I got using nodal analysis. So you can work this on your own, and then I did it both ways so you can see where you might have made a mistake. Now, what we need to do, I say here, now we need to find I short circuit, because to get Z Thevenin, we need both V open circuit and I short circuit. We just found E Thevenin, V open circuit. There it is. I need to find I short circuit now so I can form this ratio, because we had that dependent source, and you have to do this. So how do you find I short circuit? Well, there it is. Here's the same problem, except there's a short here now, and I have to find that short circuit current that's flowing from there to there, which is the branch current here. Is it going to be zero? I mean, you know, it's this current that flows in this branch. That's the short circuit current. So I defined this I1 just like I did before in that direction. IX I define going up, same way I did before, because of the plus to minus the author gives me. And I just called that, I didn't call that I2 or I3 in this, I called it I short circuit. Why introduce a dummy variable whenever we know we're solving for I short circuit? So there's my circuit. By nodal analysis at V1, I called that V1 now. It's not an open circuit voltage anymore. This is a short circuit here, so I called that V1 at that point. I just wrote my note. There's my first level equation. The only difference from this equation and the one I had before is I have a short circuit current here now. And there it is. You can look at that circuit, and you can come up with just keep it right like that. You can look at that first level equation and get it at that node. You could go from this first level equation to that second level equation. Your least common denominator is a minus J4. I just multiply each of these through by a minus J4 very carefully to clear these fractions, and I get this. Clean that up, and I get down to this point. Since V sub x is equal to a minus 4 minus V1, just like in the last problem, V sub x didn't change, but I'm going to write it like as a minus. I'm going to bring out the minus sign here and write it as a minus, a quantity 4 plus V1. I'm going to make that substitution up here. Well, those two minuses are going to cancel one another, and I get this. I take my time and I write through, and I end up with this. I end up with that expression. You might do this another way. This is the way I did it. And I rationalized that by multiplying the top by j and the bottom by j. That j times a j is a minus 1. That j times a j is a minus 1. And it cancels with that minus. That's why I have plus sign. The minus sign doesn't appear out here. And this j times a 4 gives me a j4, and the j times a j8 gives me a minus 8. I just switch this around and I clean it up, and I get this V1 is minus 4 plus j2. And there I end up with V1. This is where most students have the problem in this. They don't get that angle. They can't go from this, from that expression right there. They can't go from here to here. They don't get that angle. That angle is going to be an angle in the second quadrant. And it has to be with respect to the 0 degree axis. Too many students just go ahead and they add it to 90 degrees. They add the angle, you get here to 90 degrees. This angle is an angle from the horizontal. This tangent angle you find here, the inverse tangent of that, is with respect to the 180 degree axis, if you think about it. Look, when you're in the second quadrant and you calculate the angle, you're getting that angle right there. The inverse tangent of the opposite over the adjacent, that's that angle. You don't add 90 to that. You don't add 90 to that angle. You need this angle here. You need the angle from here to here. That's the reference angle. It's not the relative angle. So what they have to do to get this angle is they have to take 180 degrees and subtract that. They take 180 degrees and subtract this angle. Be careful. Make sure you understand how to come, when you have a negative real and a positive imaginary, make sure you understand how to get the angle, or your phasors, that's a big trouble spot. This is where most of the students mess up. Now that I know V1, if you take a look at the original circuit up here, if you know V1, you just divide it by a minus J2 to get the current. That right there it is. That's the short circuit current. And I do that, and I end up with this for the short circuit current, which is nothing more than the Norton current. Now I can form my ratio. I get my ratio, I get my Thevenin, which is 1.41 at an angle minus 45 degrees, which is equal to 1 minus J1. Therefore, to finalize this, the maximum power, the value of ZL for maximum power transfer is a complex conjugate of that. So it's 1 plus J1 ohms. And what is the value for maximum power? It's equal to E Thevenin squared over 8R Thevenin. And the E Thevenin squared you use has to be the magnitude of E Thevenin. Be careful. Students are in a hurry. They go back and they either use the magnitude on the impedance or they use the magnitude on the current. We have to go back and we have to use this magnitude right here, the 3.16, because that was your E Thevenin magnitude. We just make the substitution in here. R Thevenin is 1, and you get 1.25 watts. And that's how you work that problem out. I hope that helps.